Hello, my name's Clinton, and I'll be your guide through this second module of Day 5. We're going to talk some more about polynomials. Please don't forget to pause this presentation at any time if you need a bit more time to think about something. Last time, we saw how to perform long division of polynomials. It turns out that polynomial long division, when the thing that we are dividing by is a particularly simple function, namely a linear function, then the remainder is very easy to describe. This is known as the remainder theorem. When we divide a polynomial p of x by the linear polynomial x minus a, the remainder is just p of a, the original polynomial evaluated at x equals a. So p of x on x minus a is q of x plus p of a on x minus a for some polynomial q of x with degree 1 less than the degree of p. Unfortunately, the mathematical proof of this theorem is a little beyond the scope of this course. Let's think about what happens when the number a is a root, or solution, of the polynomial p of x. The remainder theorem tells us that p of x on x minus a is q of x plus p of a on x minus a. But by the definition of a being a root of p of a must be 0. So p of x on x minus a must just be q of x for some polynomial q of degree 1 less. Or, rearranging, we see p of x is x minus a times q of x. This is sometimes called the factor theorem. If a is a root of p of x, then x minus a is a factor of p of x. This means that if a is a root of our polynomial, we should expect no remainder upon long division. Let's have a look at an example. What happens when we divide x cubed minus x squared minus 14x plus 24 by x minus 2? Well, it's easy to check that p of 2 is 0, so this means that x minus 2 must be a factor of p of x. You should check that when you perform the long division using the method we learnt last time that you get no remainder. Press pause and press play when you're ready to continue. You might remember from last time that we saw the polynomial x to the 4 minus 2x cubed minus x squared plus 2x had roots 0, 1, minus 1, and 2. This must mean that it has factors x minus 0, or just x minus 1, x minus minus 1, which is x plus 1, and x minus 2. This means that p of x can be written as x times x minus 1 times x plus 1 times x plus 2. This is called factorization, and you should think about why this has to be a complete factorization of p of x. Suppose we have found a polynomial p of x and two numbers a and b such that p evaluated at a gives a positive answer, while p evaluated at b gives a negative answer. Then p must have a root somewhere between a and b, of course, we may not know where, because if p of x has gone from being positive to negative, it must surely have passed through 0 at some point. This very simple idea allows us to find roots of polynomials. For some polynomials, finding roots is very difficult and we need to try and approximate them. Let's look at an example. We want to try and find an interval on the x-axis of length 0.1 which contains a root of this polynomial fx equals 2x cubed plus x squared plus 6x plus 9. Notice that if we plug minus 1 into f, we get 2, which is positive, and if we plug in minus 2, we get negative 15, which of course is negative. So there must be a root somewhere between minus 2 and minus 1. The question asks for an interval of length 0.1 though, so we need to keep looking. If we look at f of minus 1.5, our calculator tells us it's equal to minus 4.5, which is negative. So the root must in fact be somewhere between minus 1.5 and minus 1. Remember that f of minus 1 was equal to plus 2. Again, using a calculator, you should check that f of minus 1.2 is negative 0.216, so our root must now be somewhere between minus 1.2 and minus 1. Now this interval has length 0.2, so we're nearly there. If we evaluate f of minus 1.1, we see that it equals 0.948, which is positive, so the root must lie between minus 1.2 and minus 1.1. It is in fact possible, but very difficult, to compute the exact value of this root. This is why approximation techniques are important, as it is very hard to arrive at this precise value. Here are some practice questions involving factorization and finding roots of polynomials. Press pause, and then press play when you're ready to continue. Here are the answers.